everyone, I'm Shubhradeep and today I'll be talking about witness maps and applications. This is a joint work with Manoj Prabhakaran and Daniel Weeks. And this work was initiated while I was a PhD student at IIT Madras. So the rough agenda of today's talk is first to motivate the problem, then to introduce the different notions of witness map, show its application to the field of leakage and tamper resilience, construct witness maps, and finally to conclude with some open problems. First, let's just briefly recall ourselves of the setting of non-interactive zero-knowledge proofs in the common reference string model. So here a prover P wants to convince a verifier that she knows a witness W corresponding to an NP statement X, and she's only allowed to send a single message to the verifier. So Nizic proofs gives us a way for one party to prove to another party in a non-interactive way that the statement X is true without revealing anything other than this fact. And the properties that we need from such a proof system are first completeness, which says that if X is true, that is, it belongs to the underlying NP language, and the prover is honest, then Bob will always be convinced. The second property is that of soundness, which says that no cheating prover should be able to convince an honest verifier. And finally, zero knowledge says that no cheating verifier will learn anything other than the fact that the statement was true. And this can be formalized with the help of simulators. After non-interactive zero-knowledge proofs were proposed, other rudimentary versions of proof systems were also proposed. And so starting with non-interactive witness indistinguishable proofs, which is a relaxation of Nizic's, which says that it is impossible to distinguish which of the witnesses was used to construct the proof. And then of witness hiding proofs, which says that a proof should hide the witness, and this makes sense even if the statement has a unique witness. Followed by probabilistically checkable proofs and more efficient proof systems in the form of schnarks, and so on. So against this backdrop of the advances of proof system, we propose the notion of a compact witness map as our first notion of a witness map. So compact witness map gives us a way to map a set of witnesses corresponding to some statement X to a much smaller set of representative witness denoted as capital S here. And the important feature is that this mapping algorithm should be deterministic. So the mapping algorithm takes as input a CRS, a statement X, and a witness from the witness set capital W, and it should map deterministically to this set X, S. And we call W as the witness set of X and S as the representative witness set. So in particular, a bit more formally, require that the setup algorithm takes as input the security parameter lambda and outputs a common reference string CRS. The mapping algorithm is deterministic and it takes as input a statement and a witness other than the CRS and outputs a proof, which we call the representative witness W star. And finally, there is a checking algorithm that takes the statement and a proof and outputs whether it accepts or rejects the proof. The properties that we need from a compact witness maps are completeness, which says that if X is true, then check should output 1, and computational soundness, which says that if X is false, then check should output 0. In particular, if a no cheating prover should be able to convince an honest verifier. And finally, we want the property of lossiness instead of zero knowledge. So in particular, we want to say that the proofs can be compressed efficiently. In other words, the size of this set capital S is much smaller than the size of this witness set for X. Our second notion of witness map is a unique witness map, which is one extreme of compact witness map. Here, we want to deterministically map all possible witnesses for an NP statement X to a single representative witness or a canonical representative witness, W star. So in particular, we have the setup, map, and check algorithms, which are the same as in a compact witness map. Additionally, we require that there should be a unique proof corresponding to each statement. This in particular says that the proof is independent of any witness that is used to construct it, and it only depends on the statement being used. So in a sense, this is equivalent to a deterministic prover and verifier non-interactive witness indistinguishable argument in the CRS model. And another way of seeing it is that UWM is an alpha lossy CWM where alpha is 1 because the support is just a canonical witness. And we want completeness and computational soundness to hold as in a compact witness map. Finally, we propose our final notion of witness maps, which we call a dual mode witness map. This allows a dual mode property for the compact witness map. In particular, this is a tag-based notion where the setup algorithm takes as input a branch or a tag B other than the security parameter and outputs a CRS along with a trapdoor. We call this branch B as an injective branch. The mapping algorithm is deterministic as usual, and it also takes as input a branch to evaluate the representative witness. And we want completeness, which says that on all branch, if the map was constructed correctly, check should output 1. We want the property that the injective branch B is hidden by the CRS, which we call the hidden branch property. We also want extraction on the injective branch B. In particular, any proof or witness, representative witness that is constructed using map on the branch B allows for extraction with the trapdoor TD. Moreover, we want a stronger property of soundness, which we call knowledge soundness, which says that on the branch B, it is if the adversary at all comes up with some statement and a proof corresponding to it, then it must know the witness in the first place. And finally, we insist on a stronger form of lossiness, which we call cumulative lossiness, which says that if you evaluate the map on all branches other than the injective branch, in particular, if you evaluate the map on arbitrarily many lossy branches, the amount of information that you reveal about W is at most alpha. So the loss does not accumulate with the number of evaluations of the map, but it is bounded by some alpha, irrespective of the number of evaluations under different lossy branches. Now we show how to construct a deterministic leakage and tamper resilient signature given a dual mode witness map. For this, we resort to the bounded leakage and tampering model of Damgard et al. From AsiaCrypt 2013. And in particular, we strengthened the BLT model with the following feature, that the signing randomness is now open to leakage and tampering attacks. However, we do assume that the code and the public parameters are not subject to tampering, as is the case in all previous works on leakage and tamper resilient signatures in the BLT model. To be more precise, we consider a setting where there is a challenger and an adversary, and we consider the selective unforgeability game where the adversary gives the message M star ahead of time, and the challenger produces the public parameters by running the setup with the message M star, and produces the signing key pair and gives the public parameters and a verification key to the adversary. Then, as usual, the adversary can ask different messages to the signing oracle and get signatures corresponding to them, and the state of the challenger is updated by augmenting the random coins that are used for signing each message. And this stage can continue arbitrarily many times. Now the adversary can also ask for signatures under tampered signing key. In particular, it asks TI and some M prime, where M prime is not equals to the challenge message M star, and Ti in some sense tampers your state, and the adversary gets tampered signature under the tampered signing key and the tampered randomness. And this can also happen arbitrarily many times as long as the following restriction holds. The functions Ti come from some class of tampering functions, and the number of Ti that the adversary can ask throughout his lifetime is bounded by some parameter T. So in particular, the adversary can ask T tampering queries, but for each tampering query, it can ask arbitrarily many signatures. Finally, the adversary can also ask for leakage queries on the secret state and get the random variable corresponding to applying the leakage function on the state so far. And this can continue arbitrarily many times, subject to the restriction that the sum of the leakage functions does not exceed beta. So we note that beta and T are parameters of the system and should be fixed ahead of time. Finally, the adversary, after getting all these outputs from these different oracles, should come up with a purported signature sigma star, and the adversary wins if the signature verifies. So we note that at this point, that since the randomness of the signer is open to leakage and tampering attacks, there is no hope that I can protect against arbitrary tampering attacks. So we, in particular, the class of tampering functions that we consider is probabilistic polynomial time functions. So in particular, the adversary can just reset the random coins to all 0 strings. So this will necessitate a deterministic solution. So now we show that combining a dual mode witness map along with a second preimage resistant function, how do we get a deterministic leakage and tamper resilient signature? So the setup algorithm of the signature samples a random branch B and runs the setup of the dual mode witness map using this branch B. So recall that the dual mode witness map is a tag based notion where the setup algorithm takes as input a branch B and outputs a CRS and a trapdoor. So in the signature setup, the branch is sampled randomly, and the public parameters consist of the CRS along with the description of the SPR function. The key generation algorithm consists of sampling a random preimage of H, and the verification key is H of X. And we want that H is a sufficiently compressing SPR function. The signing procedure is now computing a representative witness under the mapping algorithm of the dual mode witness map corresponding to the statement that the signer knows a preimage corresponding to Y, and the signature is just the representative witness of the DMWM. The verification is as usual. It runs the underlying check algorithm of the DMWM to verify the signature. The proof of selective unforgeability follows in a rather straightforward way, in the sense that in the proof we set the branch B to be M star. Recall that we only target for selective unforgeability, but the adversary gives M star ahead of time. So in the proof we set the branch B to be equals to M star, and note that when the adversary produces a forgery under M star, it should be extractable using the trapdoor, since this is the injective branch. And now since the adversary cannot ask for signatures under M star, this corresponds to evaluation of the DMWM under different lossy branches. At this point, the cumulative lossiness property of DMWM ensures that the signatures are cumulatively lossy evaluations of the witness, which is X in this case. And hence, X still has a lot of entropy in it. At this point, when the adversary produces a forgery, we use the extractor of the DMWM to extract a hopefully second preimage of Y. Now we argue that the extracted preimage X prime is indeed a second preimage because the signatures did not reduce the entropy of X too much. And this contradicts the SPR property of this function, H. Having shown the application of DMWM, we now turn to constructing a dual mode witness map. So to do this, we first introduce a new notion of lossy trapdoor function, which we call a cumulative LTDF, and we also introduce a generalization. So to briefly recall, note that LTDF allows to sample a function in two ways, either in an injective mode or in a lossy mode, such that in the injective mode, the evaluations of the function can be efficiently inverted using a trapdoor F inverse, whereas in the lossy mode, a lot of information about the input is lost on an average. And these two ways of sampling the functions are computationally indistinguishable. Now we ask the following question. If we evaluate different lossy functions on the same input x, what can we tell about the information that is revealed by x by this joint evaluation? So in particular, it's easy to see that if the number of evaluations is greater than n over k, then x is completely determined. So this says that if you evaluate different lossy functions on the same input, you have no guarantee that the input is hidden. So now we introduce a stronger property of lossy trapdoor functions, which we call alpha cumulative lossiness, similar in spirit to a dual mode witness map. Now this says that it does not really matter how many times you evaluate the lossy trapdoor function. The guarantee is that the amount of information that is revealed about x is at most alpha, and alpha is a parameter of the scheme. So in our paper, we show how to construct such a cumulative LTDF based on the DDH and the LWE assumptions, and I encourage to see our paper for the construction. We also introduce a richer abstraction of a cumulative LTDF, which we call a cumulative ALL-LossyBut-One trapdoor function. So this is similar to a CLTDF, but in the sense that it is a branch-based notion. And we require the property that only one branch is injective and all other branches are lossy. And this injective branch is used to sample the function f and f inverse. So note that this property is actually complementary to the property of all but one lossy trapdoor functions that is known from the literature. So on injective branch, we want completeness. We want cumulative lossiness on the lossy branches. In particular, if I evaluate the function on any branch other than the injective branch B star, then the function is alpha cumulatively lossy. We also want the hidden injective branch property, which says that the function f hides the branch B star. So in our paper, we show how to combine a cumulative LTDF along with IO to construct a cumulative ALL-LossyBut-One TDF. So given a cumulative ALL-LossyBut-One TDF and a compact witness map, we show how to construct a dual mode witness map. So recall that the setup of a dual mode witness map takes as input an injective branch B star. So to run the setup, we first run the setup of the CWM to generate a CRS for it and sample a function f along with this trapdoor f inverse using B star as the injective branch of the trapdoor function. And we set the CRS to be the description of the function and the CRS under the CWM. And the trapdoor is f inverse. So the mapping algorithm takes as input a branch B, x, w, and evaluates the lossy trapdoor function on the witness w and computes a proof corresponding to the statement that y was computed correctly and xw belongs to the underlying NP language scriptel. And finally, the representative witness for the dual mode witness map is y and the proof computed under the compact witness map. And the extraction is straightforward. Given a y and a proof w star under CWM, the extraction algorithm uses the trapdoor of the LTDF to extract from Y. So it's easy to see that the soundness property of CWM translates to the soundness for the dual mode witness map. The lossiness properties add up, in particular if we have an alpha lossy CWM and a trapdoor function that on average loses alpha prime information about the input, then we get an alpha plus alpha prime cumulatively lossy dual mode witness map. And finally, the hidden branch property of DMWM follows in a straightforward way from the hidden injective branch property of the TDF. And finally, as the last missing piece, we didn't show how to construct a compact witness map. So in this part, we show how to construct a CWM from indistinguishability obfuscation. But for that, I need to introduce punctured digital signature. So this is an augmentation to normal signatures in the following way, that you could puncture the signing key at any message M star to get the punctured signing key. And now you want the following consistency property, that for all messages M that are different from M star, it does not really matter whether you evaluate the signature using the original signing algorithm, using the master key SK, or you use a punctured signing algorithm using the punctured signing key on the same message M. So in particular, this says that both sign and punctured sign are deterministic. The security property that we need from such a signature scheme are punctured selective unforgeability, which says that the adversary cannot produce a forgery sigma star on the message M star even if it is given a punctured signing key, where M star is declared before in the selective unforgeability game. So in our paper, we show how to construct a consistent PDS from the sole assumption that one-way function exists. So previous constructions of Bellare et al. Relied on sub-exponential IO and sub-exponential one-way function to construct such a consistent PDS. And our idea is very simple. We show that this paradigm of constructing signatures from one-time signatures extends to this setting if we use a punctured PRF instead of a normal PRF. So now I show that how to tag a punctured signature along with IO to construct not only a compact witness map, but actually the stronger variant of it, a unique witness map. So the setup samples a key pair of PDS, and the CRS of UWM is the following obfuscated program that checks whether the statement and the witness belongs to this relation, and then it signs the statement X using the signing key of the PDS, which is hardwired inside it. The mapping algorithm consists of simply running this obfuscated program, and the representative witness is nothing but a signature under the statement X. And the checking algorithm consists of verifying the signature on the statement X. So to see why this is sound, so we'll be dealing with the notion of selective soundness, where the adversary gives the statement X star on which it wants to break soundness. So given X star, note that I can puncture the signing key at X star. In the next hybrid, I change the obfuscated program by including the punctured key instead of the normal signing key. And the security of IO and consistency property of PDS tells us that we could do this switch. And finally, the selective soundness follows from the selective unforgeability of PDS. Now I'll mention some open problems. So the first and the most important open problem is that can we construct a compact witness map from standard assumptions? So in the last section, I showed you how to construct a UWM from IO. And in our paper, we show that a UWM in fact implies witness encryption. So in that sense, UWM is the newest member of Fustopia and arguably the one with the simplest definition. So it seems unlikely that one can construct UWM from standard assumptions, but it might still be possible to construct compact witness maps from standard assumptions. So the question that's also interesting to explore is that does compact witness map with super polynomial image size imply witness encryption. So in particular, at this point, we don't know whether compact witness map can at all be constructed from standard assumption, or it is also a member of Officetopia. While it is easy to see that a CWM with polynomial image size do imply witness encryption, but we don't know nothing beyond that. We also, so constructing a cumulative ALL-LossyBut-One trapdoor functions from standard assumption is also an interesting open problem. And finally, we want to explore more applications of witness map, given that this is a new primitive and potentially it might find more applications in seemingly unrelated areas other than the field of leakage and tamper resilience. Having said that, I would want to conclude my presentation and thank you for your listening to the talk.